Okay guys, in the previous video we discussed the drawback of L filter and C filter, and we discussed there that these two filters cannot be used in a circuit where we have a variable load resistance, like the load resistance is varying with passage of time or with time. Now for such kind of load resistance we use another kind of circuit filter which is called LC filter. Its alternate name is also L section filter, or we can also call it choke filter. Now here is the circuit diagram of this LC filter. It is obvious from its name that there will be two components. Now one is inductor and the other one is capacitor. And from our previous discussion we know that inductor is always connected in series while capacitor is always connected in a parallel combination with the load resistance. Now why we connect the inductor in series? Because this inductor allows DC current and block AC current, and similarly this capacitor which block DC current and allow AC current. Now let's suppose we have the output here at this point after passing through the rectifier. Here the output contain both AC and DC component. The output contain both AC and DC component. So it contain both AC plus DC component. Now once this pulsating current or this ripple DC current which contain both AC and DC component passes through this inductor, then this inductor block the AC current and allow the DC current. But in the previous video, like in the L filter, we also discussed that might be there is a possibility that a small portion of this AC current, like the first harmonic we discussed there, that might be that will passes through this inductor also. So in here we have almost the current will be DC current will be there, because this inductor block the AC component up to some extent, like it block the it block the AC current above second harmonics, like third harmonics or fourth harmonics or fifth harmonics, while might be the second harmonics will pass through this inductor because the frequency of second harmonics is small. Now once this almost DC current reach here, then it either passes through this capacitor or it will pass through this inductor. But this capacitor only allow AC current, so the remaining part of AC component, some part is blocked here, might be a small variation will pass through this inductor, so that variation will pass through this inductor. So after passing that variation through the inductor, here on this load resistance we have almost a constant DC current appear. So here we have the voltage and the load resistance. So this block the AC and allow the DC. Now there is some variation in the DC, so that variation will pass through this capacitor. So here we have purely DC current appeared here. So this inductor, this LC filter provide more ripple reduction as compared to L filter or C filter, which results more DC component in the output and very small value of AC component in the output also. There are small AC component, but the variation is very small, so the current in the output is almost approximately DC. There is a small variation, but we will discuss it later. Now we will calculate the ripple factor for this LC filter. Now according to Fourier transformation or Fourier series, the output of full wave rectifier, like here the output, this one, the output voltage is given by this relation V naught, which is equal to 2 Vm over pi plus no sorry, it's minus 4 Vm over 3 pi, and we have the first harmonic term cos 2 omega t, and then we have minus 4 Vm over 15 pi, and we have the second harmonics, which is cos 4 omega t, and then we have minus the fourth harmonics, and then we have the fifth harmonics, and so on. Now here this one is the DC component of the voltage, like here it's contained both DC and AC. So the DC component is given by this one, and this one up to here are the AC component. Now the resistance offered by the inductor, which is called inductive reactance XL, is equal to omega times L. This is the resistance offered by the inductor to the AC current or to the current, any kind of current. Now for the second harmonics, here this is the first harmonics, because here we have cos also, but the cos is 0t. So cos of 0t is already 1, so we can't put it here. So this is the first harmonics, this is the second harmonic, this is the third harmonics, and then we have fourth and fifth harmonics. Now for the second harmonics, the frequency is, the net frequency is 2 omega. So the inductive reactance for second harmonics is 2 omega L. Similarly for third, the inductive reactance XL is equal to 4 omega L. And similarly for the fourth, the inductive reactance will be, for fourth, the inductive reactance will be 6 omega L. So as we move from lower harmonics to higher harmonics, this inductive reactance or the resistance provided by this inductor also increases. So it means that this inductor will block these third, fourth, and the higher harmonics, and might be the second harmonics may pass through the inductor. Because the inductive reactance is smaller for the second harmonics. So the inductor offered a small resistance to this part, while it's offered high resistance to this one or the other higher terms. So these terms will be blocked by this inductor, and this term might be, there is a possibility that this term may pass through the inductor. So the output here, which is almost DC, but it also contains a small portion of AC current also, a small variation. So the output after passing through the DC through the inductor will be, it will be V naught, which is equal to 2 Vm over pi, and then we have minus 4 Vm over 3 pi into cos 2 omega t. If this is my equation number 1, then this will be equation number. Now this is the output after passing through the inductor, so I can also name it VL, the voltage after passing through the inductor L. Now the DC component of the voltage VDC is this one, which is 2Vm over pi. Then the DC current will be IDC, which is equal to DC voltage divided by the load resistance RL. So its value will be 2Vm over pi RL. This is equation number 3. Now next we will calculate the AC current or the AC component of voltage. The AC component of voltage will be VAC, or we call it V ripple. The ripple voltage will be this 4Vm, this one, over 3 pi into cos 2 omega t. So this is equation number 4. Now the AC current will be represented by this symbol IAC. We call it the ripple current. The current due to this small variation is equal to peak value of voltage Vm divided by impedance, where Vm represent the peak value of voltage and the peak value of voltage is this one, which is 4Vm over 3 pi. Here Z is called impedance, or it is basically the resistance offered by, there are 3 components now. One is the inductor, the other one is the capacitor, and the other one is the load resistance. So it is the resistance offered by, it's the impedance or resistance offered by inductor. The resistance offered by inductor is called inductive reactance, or by capacitor, which is called capacitive reactance, and load resistance R. Now if you look at here, this load resistance and capacitor, they are parallel to each other, while this inductor is in a series with this parallel combination. So our AC current or ripple current IR is equal to 4Vm divided by 3 pi into Z. This is equation number 5. Here Z, which is equal to XL plus XC, which is in parallel combination with load resistance I. Like the impedance is equal to parallel combination of XC and RL series with load resistance. How we can read it? Z is equal to parallel combination of XC and RL series with XL. Now to suppress the high frequency component like higher harmonics, like this third harmonics or fourth harmonics, we know the opposition offered by the inductor, like the opposition offered by the inductor increase with increasing the frequency, because XL is equal to omega L. So this opposition offered by this inductor is increased with increasing frequency, but it will also increase with increase in the value of L. So the value of XL, the value of this XL is very high as compared to the resistance offered by this capacitor or by the parallel combination of capacitor and this load resistance. So as compared to this XL, the resistance of the parallel combination of this XC and RL is small, so we neglect this parallel combination. So overall we can write that the impedance Z is equal to XL. So if we put this value in equation 5, we get IAC. I can write here IAC I ripple is equal to 4Vm over 3 pi into XL, and I call it equation number 6, where XL is equal to, we just consider the second harmonic and the frequency in the second harmonics is 2 omega, so XL will be 2 omega L. This is equation number 7. So now equation 6 can be written as, equation 6 can be written as 6 implies IAC, which is equal to IR, which we can write it as 2 over 3, and then we have 2Vm over pi into 1 over XL. This is same as equation 6. So IAC I ripple is equal to 2 over 3. This 2Vm or pi is basically the DC voltage divided by XL. This is equation number 8. Now this represents the value of AC current passes through the inductor. This represents the AC current passes through the inductor. I will stop here and I will continue in the next video.